Rotating spherical shell. When a rigid charge distribution with charge Q and mass capital M rotates about an axis, its magnetic moment mu is linearly proportional to its angular momentum L, with mu is equal to gamma times L. The constant of proportionality, gamma, is called the gyromagnetic ratio of the object. We can write gamma as gamma equals to G Q over 2m, where G is a dimensionless number called the G factor of the object. Consider a spherical shell with mass capital M and uniformly distributed charge capital Q, centered on the origin O and rotating about the z-axis with angular speed omega. Part A, a thin slice with latitude theta measured with respect to the positive z-axis, describes a current loop with width r d theta and radius r sine theta as shown in the figure. What is the differential current di carried by this loop in terms of capital Q omega, capital R theta and d theta? Okay, so we have at this latitude a strip you can see here of width r d theta, and it has a radius r which is going to be r capital R sine theta. The sigma charge density, surface charge density, is the total charge Q, because this is a spherical shell, divided by the surface area 4 pi capital R squared. Now, what is the area defined by this strip, dA? It is its circumference, 2 pi r, multiplied by its width, r capital R d theta. So it is 2 pi r capital R d theta, where I noticed that the radius of this circle is capital R sine theta. So this is 2 pi capital R sine theta capital R d theta. Therefore, I can see that the differential area here is 2 pi capital R squared sine theta d theta. All right. Now, what is the charge carried by the strip dq? It is sigma surface charge density multiplied by the area dA. So sigma, the surface charge density, is capital Q divided by 4 pi capital R squared, and for dA I write 2 pi capital R squared sine theta d theta. Now you can see the pi's cancel. This 2 will get rid of this 4, make it 2, and also I have r squares disappearing. And therefore, I'm left with a dq that's equal to capital Q over 2 sine theta d theta. And this spherical shell is rotating with angular speed omega, which is 2 pi divided by its period of rotation t. So t is equal to 2 pi divided by omega. Therefore, the current carried by the strip, dI, can be written as the charge that revolves in one period, dq divided by t, which is q capital Q over 2 sine theta d theta and omega divided by 2 pi. So that's 1 over the period, omega divided by 2 pi. So I can write my final answer, dI is equal to Q, capital Q, omega sine theta d theta divided by 4 pi. So that's the current carried by this strip. So let's move on to part B of the problem. The differential magnetic moment contributed by that slice is d mu, which is its area multiplied by di, where area is pi r square. It's the area enclosed by the loop. Express the differential magnetic moment in terms of capital Q, W, capital R, theta, and d theta. Okay, so this d mu, the magnetic moment created by this rotating strip, is a times di, which is pi capital R sine theta parenthesis squared di. And in which direction is it? So using the right hand rule, we follow the current with our four fingers. The thumb points in k hat direction, so we can see that. Therefore, this is going to be in k hat direction. That's the direction of the magnetic moment. Now we can write it as a vector. d mu is equal to pi capital R square sine square theta. Now I have di, which is capital Q omega sine theta d theta divided by 4 pi, and this is in k hat direction. So you can see that the pi's will disappear here. And I have found the direction of the magnetic moment using right hand rule. Now I can write my final answer for the magnetic moment. d mu is equal to capital Q omega r square sine cube theta d theta divided by 4 in k hat direction. So you can see that here I have a sine square theta and sine theta, so it makes sine cube theta. Let's move on to part C of the problem. Integrate over the angle theta to determine the magnetic moment mu. So if I integrate over this angle theta, starting from theta equals to 0, going all the way to theta equals to pi, I will have all of these strips counted. So I just need to integrate d mu over theta from 0 to pi. So that's capital Q omega capital R squared over 4 integral from 0 to pi sine cube theta, which is sine theta sine square theta d theta in k hat direction. So this will give me Q omega capital R squared divided by 4 integral from 0 to pi. For sine squared theta, I'm going to substitute 1 minus cosine squared theta. So that gives me sine theta minus sine theta cosine squared theta d theta in k hat direction. Okay, so let's call u cosine theta. Then you can see that du is minus sine theta d theta. So let's perform this integral from 0 to pi sine theta minus sine theta cosine square theta d theta. The integral of sine is minus cosine, so that gives me minus cosine theta. And then I have plus this integral u square du. So that's going to give me minus cosine theta plus u cube divided by 3. Of course, I will have to evaluate this between 0 and pi. So that remains to be done. This will be evaluated between theta equals 0 and pi. Okay, so the answer is minus cosine theta plus cosine cube theta divided by 3, which will be evaluated between 0 and pi. So that gives me cosine pi, which is minus cosine theta minus cosine pi is 1. And then I have cosine cube pi over 3, which is minus 1 over 3. Cosine 0 is 1. This is going to be minus 1, but minus 1 will become plus 1. And here it is cosine cube of 0 divided by 3, which is 1 over 3 plus 1 over 3. But since I'm subtracting, it's minus 1 over 3. So this is 2 minus 2 over 3, which is 4 over 3. So I can write my total magnetic moment vector now. It is Q omega capital R squared over 4 multiplied by 4 over 3 in k hat direction. So that gives me my final answer for the magnetic moment. Q omega capital R squared, these 4's cancel, divided by 3 in k hat direction. That's the total magnetic moment of this rotating spherical shell. Looking at part D, what is the magnitude of the angular momentum, L? Okay, so we will start working on the angular momentum now in part D. Angular momentum of a solid object is its moment of inertia times its angular speed omega. So I is going to be the moment of inertia of the shell. That's for rotations about its central axis. So how do I find the moment of inertia? It is integral r square dm, where r is the distance between the mass element and the rotation axis. And dm, the mass of a differential element here, is its total mass divided by the total surface, that's the mass density, multiplied by dA. So this is going to be capital M divided by 4 pi r squared. And for these strips, the dA is 2 pi r squared sine theta d theta, as we have found in the previous part. Again, we have this 2 pi and 4 pi cancelling, 2 remaining here, and this r squares cancel. So this is m over, capital M over 2 sine theta d theta. That's our dm. So the moment of inertia, I, is then the integral from 0 to pi, all such strips. They each have a mass m over 2 sine theta d theta, and they are at a distance r sine theta from the rotation axis. So you can see here, each mass element consisting of the strip is at the same distance from the rotation axis, which is r, that is capital R sine theta. So this is capital R square sine square theta, capital M over 2 sine theta d theta. That gives me capital M, capital R squared over 2, integrate from 0 to pi, sine cube theta d theta. This integral I have evaluated in the previous part. The answer is 4 over 3. So mr squared over 2 multiplied with 4 over 3. So here I have a 2 remaining on top. The moment of inertia is 2 over 3 capital M capital R squared, which means I can write its angular momentum L as 2 capital M capital R squared omega divided by 3. What's the direction? It's in the same direction as omega using the right hand rule. The four fingers curl in the direction of omega. The thumb points in k hat direction. So this is going to be in k hat direction. So that's the angular momentum. Part E, determine the gyromagnetic ratio gamma. Gyromagnetic ratio is the ratio of the magnetic moment to angular momentum. So gamma is mu divided by L. Mu we have found in part C, Q omega capital R squared over 3. This was the mu we found. And angular momentum we found in part D. So it is 1 over L, which is 3 over 2 capital M R squared omega. So the 3's cancel, omegas disappear. I'm left with also the R squares will disappear. I'm left with a Q over 2M. So the gyromagnetic ratio is capital Q over 2 capital M. All right, so in part F, the gyromagnetic ratio can be written as a multiple of Q over 2M, the coefficient being the G factor, Q over 2M multiplied by G. Here, obviously, this G factor is equal to 1. So, we can conclude that the magnetic moment is gamma times L, so it is Q over 2M times L, the angular momentum. So in this problem, we looked at a rotating spherical shell. First of all, we go to a latitude defined by this angle theta, and there's a strip there whose width is capital R d theta. So if we vary this angle by a small amount d theta, we will find this width, that's d theta. And the circumference here is 2 pi r, which is 2 pi capital R sine theta. Capital R cosine theta is here. Capital R sine theta is the radius. The surface charge density for the spherical shell is the total charge divided by the area, 4 pi capital R squared. And the area of this strip is dA, which is its circumference multiplied by the width, 2 pi r times capital R d theta. And the charge it contains is the surface charge density multiplied by its area. And if we divide it by the period, where the period is 2 pi over omega, we find the current carried by this strip. The corresponding magnetic moment for this current loop is the area multiplied with the current it carries. The area defined by this strip is capital R sine theta parenthesis squared times pi, so it's pi r squared multiplied by di, and the direction of the magnetic moment is found using the right hand rule. It's in k hat direction. If I integrate this magnetic moment over the angles 0 to pi, then I will have accounted for all of these strips and found the total magnetic moment in k hat direction, which is the answer in part C. The moment of inertia of the spherical shell for rotations about the central axis is integral r squared dm, where r is the distance from the rotation axis, capital R sine theta. dm is the mass of that strip, which is the mass density multiplied by its area. And the angular momentum is the moment of inertia times the angular speed. So that's what I find here. The ratio of the magnetic moment to angular momentum gives me the gamma factor, Q over 2m. And I see that this gamma factor is a multiple of Q over 2m, which is called the G factor. And G factor is equal to 1 in this case.